Everyone, I am Aatman from Tatte. I think the previous speakers, Digvijay and Dr. Geeta, covered a lot of it very well. So apologies if there is some repetition. Me and Priyash are broadly just going to talk about open source deepfake detection. There was some exploratory analysis that we did, and we tried to test these models and some of our takeaways and learnings by looking at open source deepfake detection. So I'm Aatman. I work as a software developer at Tatte.
I'm Priyash. I'm engineering intern at Tatte.
Yeah. So, a lot of the fact checkers and organizations in the room who work on detecting AI generated and manipulated content often use automated or semi-automated tools to detect such type of contents. They are a mix of proprietary, closed and also open software. So we were generally curious, what is the performance of these open source machine learning models for deepfake detection? How easy is it just to set up, run and do some inference with them? What are their capabilities, as in what type of deepfakes are they able to detect? And we also wanted to see what is the trade-off between a proprietary and a closed source model. Of course, we know that proprietary and an open source model. We know that proprietary tools they show state of the art and high performance. But what's the gap between an open source and a proprietary model?
Right. So Deepfake-o-Meter is a platform created by University of Buffalo. So researchers and engineers created this platform where they hosted 18 state-of-the-art models across different modalities like video, image, and text. And it's an active platform, really simple to use. We selected few models from this platform to test on our custom data set.
Yeah. So another reason of deliberately looking at a project like this was we also thought that they did the background of choosing which are the best models. So we said maybe this is a good start for us. So when we started looking at the models, we started reading the model reports, the papers, the Hugging Face cards, looking into the training data sets. As also Digvijay and Dr. Geeta mentioned, that we could broadly see that deepfakes has certain types, where if it's an image and video, generally it's facial attribute manipulation, either by swapping the face or either by making some changes in the lip or lip sync. And when it's audio, generally it's voice cloning, or you're dubbing a certain voice, or you are using AI to generate speech from given text. So these were the common themes and patterns we could see. And if it's a mix of both, if it's a mix of image and audio, as also the previous speakers mentioned, that sometimes the manipulation is only in audio, while the video is normal. This is another feedback that we also got from the DAU, and we sort of started taking the direction and looking at audio. So audio was the first modality that we explored. And when we started looking at the types of deepfakes, we also then dive deep into the technical methods used to detect them.
Right. So for videos and images, mostly when we see social media platforms, we see that there's some sort of face swapping, lip sync, and the methods used for deepfake detection for these kind of things, where basically for images we look at spatial structure, for video we look at a temporal structure across the frames, and sometimes we also see inconsistencies between the two. So whatever model that we looked into were novel in their approaches. So each one was different, and sometimes we also look at the embeddings level. So very low level, sometimes we look across the frames.
So the broader thing that we realize is that each team or developer developing their own, let's say a machine learning model to detect deepfakes, had a very specific approach that customized to their task and usage, right? Either they were taking a simple approach of just training a machine learning model, or they were looking at specific features in an image and audio, which also Digvijay talked a bit about. And when we looked at audio, the same thing was happening. Some people were looking at some properties in audio, some features in audio, some technical features in audio, while others were just doing general training for their use cases. Or people were just doing an ensemble of models where they were using multiple models to get the job done. So what we did was, we just created a small data set of roughly 50 audio files. It was a balanced data set. It was a mix of synthetic audio files and non-synthetic audio files. And then from the Deepfake-o-Meter project, we selected the best performing audio model and we just started running. And this data set was in an Indian context, as in Indian voice, Indian audio and an Indian context. We just quickly want to play and sample. So we synthetically generated the voice of Arvind Kejriwal, and the model could not detect it. Now I'll just play the voice. Yeah. Sorry.
I think the file is not.
The file is. It's mine.
You might not have time for request access.
Okay, so essentially it was an AI generated voice which the model was not able to detect. The same thing when we did, we chose another model called Whisper. It's a popular audio detection model, and when we ran it against a synthetically generated audio, sometimes it used to say yes, it can detect, and sometimes it used to say no. So Priyash can just talk.
Right. So we have marked the outcome as yellow because the output wasn't deterministic. So in most of these models, we have some sort of parameter which sort of gives model creative freedom to choose from different samples. So in LLMs we have temperature. Similarly, Whisper model created by OpenAI also has that parameter called temperature. So that's why we have marked it as yellow, because sometimes it gives result as deepfake and sometimes it doesn't.
Yeah. But one thing that we also realized, since the model was open, we could do some of our own tinkering and our own debugging as to why is it happening. We tried to look at the data that the team used. It was a fine-tuned model, and so we just tried to do some more debugging. A similar thing with video. I'll just try to see if the video can play. So we just chose a deepfake video from YouTube and
Here is Joe, my best friend.
and uploaded it to. This is not this is more of a deepfake detection method that was used, not a machine learning model per se. And the platform just said that it's an 20% likelihood. And then also we did our own analysis as to why this is happening. But it can well, I can go a bit later into it. And similar thing happened when we just ran it on a different deepfake video where it just said 40% likelihood. The one thing that it bugged us was what does this 40% likelihood mean? And the website just said, oh, you have to read it in your own context. But that doesn't say much to me as a user. And yeah. So just final 2 slides, we can just share some of our larger takeaways from this exercise.
Right. So most of the images and video models only supported perturbations or edits made on the video, synthetically created samples, which only change the facial structure. So if you sort of made a deepfake video of a unicorn and posted it in models like this, it won't actually sort of give good results. And similarly, also these models also face challenges when we give them samples that were not in their training sample. So in the training set, if the sample isn't present, the models will perform very badly.
Or also on unseen real world images like social media data, as also previously mentioned by the speakers. This was also validated by the recent release of the deepfake in the wild dataset by True Media. True Media also created a deepfake dataset from social media, and they saw that a lot of open source models fail to perform well on unseen images. Another thing was that similar observation for audio based models. Is what also Digvijay mentioned, that academic research is not equal to real world research. Since they were trained on very good quality audios or like proper audios, they failed on real world examples. Another key takeaway was just looking at open source models also helped us a lot, as there was a lot of visibility into the training data. We could do a lot of debugging. We could understand why this is happening, why some results are working well, why some results are not working well. This is a continued exercise that we are doing. We have also written a blog post about it if you are interested. But yeah, that's it. Thank you.